Okay. Can everyone hear me? Everyone hear me? All good? Okay. So, good evening, everyone. Welcome back to your weekly intro course, regularly scheduled program. Welcome to week 2. So, today we'll be starting out with our deep learning unit. And just quick, same as last time, Unit 2 is now available in the Megadoc. You should be able to find the project, the non-technical project, and all the resources, plus synthesis questions that you need on there. Same as last week, one synthesis question due in the channel on Tuesday, and then all of them, plus the project, due on Thursday in the submission form. And there's the attendance QR code, so everyone take a second, scan that, get your attendance for the day. And if you miss it now or whatever, know that in our intro course resources channel within Discord, all these links are there. So you will have the all slides link, the course website link, the attendance form, and the submission form. So you should always be able to find them, and the attendance form will always remain open during our meeting hours. So yeah, if you're not able to scan it, the link will be the same and you will be able to fill it out. So just fill that out. And then Varun will give a lecture today on deep learning. I think you guys should be excited. He's very good at this stuff. So yeah, just take a few minutes. Any questions? Any administrative issues? Anyone? Anything? All good? Okay. Here, Varun, we'll now start then.
Awesome. Okay. This is super exciting because this is one of my, hopefully this isn't too loud. This is one of my favorite lectures to teach just in general, Introduction to Deep Learning, which if you're not familiar with what that is, you will be by the end of this lecture. I've given this like a couple times now in like different formats, and I finally was like, okay, I need like a really good slide deck for this. So I'm excited to present this. So you know what, honestly, let's just dive right in. So this lecture is going to be going over a very basic introduction to deep learning, how it differs from machine learning, because I think that's an important distinction. And also I'm going to go over what I like to think of as like the poster child of deep learning, which is something that you may or may not have heard of, a neural network. And we're going to be going into like how a neural network works exactly and how they learn. And then, of course, after this lecture, for the following week, you'll be checking out the resources that we have on our website, and those have some wonderful videos that have really nice animations and graphics to help you get a super nice like understanding of how exactly these neural networks work. So, I guess I already went over this already, so I'm going to go to the next slide. So, deep learning. Can someone, like without necessarily looking at this slide and just reading off of it, tell me what in their head they think of when they hear the words deep learning? Anybody? Learning like a human does. Okay, that's one way to think about it. Learning like a human does. When you say like a human does, what is different than like how a machine would learn? Like where's the distinction there in your mind? Okay. Okay, so there's like some kind of feedback loop going on there. Yes. Okay. You brought us something there that you'll hear a lot. Linearity or non-linearity. That's something to have in your mind. I'll go over like what that is exactly by definition by the end of this. But as far as I understand, something about deep learning seems to be inherently more complex in everyone's minds. And that's true. Deep learning is a subset of machine learning, meaning that like the field is contained within the larger field of machine learning. Most things that are machine learning, everything that is deep learning is also just kind of in the bubble of machine learning. Because, as Kellen said last week, machine learning generally is just getting models to train themselves based off of data. And that's also what we're doing in deep learning, but we also have some kind of like more specialized things that deep learning can do. We have greater computational intensity, increased power on like the patterns that we can recognize. However, we also have fewer theoretical guarantees, which I'll go into later. It's more of like kind of like a wishy-washy area as to like, can it really learn this? Are we sure it's doing this? How interpretable is it? It's not fully or as solidly understood as it is in machine learning. We also make a lot of empirical decisions, definitely more so than just in general machine learning. Most of the things in machine learning are, we chose this architecture because it is perfectly built to solve this style of problem. But in deep learning, we're like, oh, it tends to work, so let's keep using it. It's more of an empirical science as of the moment, but there's definitely some theory getting into it now. There's this term I mentioned earlier, nonlinearity or non-convexity. I'll go over that later, no need to go over it now. And finally, deep learning is generally more data hungry. So that's like kind of like the really high level, like what you should kind of go into this lecture expecting me to go over. Any questions based off of that? Any comments? History-wise, so the first neural network, I believe, so if we were to look at it from a computer vision standpoint, which some people do, ImageNet was one of the first big challenges that deep learning showed its kind of like fangs in, basically. Traditionally, and I'll go over this, we did a lot of like human engineering to try and solve the ImageNet challenge, which is basically classifying a bunch of pictures into certain buckets. But the first time deep learning did this, and I wish I could tell you the exact date, but I think it's around like maybe late-ish 2000, like mid 20, early 2010s, maybe late 2000s, I believe, like people started using the idea of deep learning to actually solve ImageNet. Don't quote me on the exact date, but it definitely was in the 2000s. But the ideas had kind of slowly been built up even in like the 1960s and beyond. But the first time it really kind of sprung onto the scene was with ImageNet. So if someone finds when that paper was released, then let me know on the exact date. But yeah. So the question was, does it seem like a recent, I guess, leap because of like the increase in compute and technology? The answer is definitively yes, because as you'll see, what happens behind the scenes is not actually incredibly complex in a neural network. However, it just requires a lot of data, and it would be impossible to do these calculations by hand. So we needed compute. And because these neural networks like are so data hungry and can actually make use of all the data, they became powerful when we had large data sets like ImageNet to train off of. So yeah. But we're kind of getting into the weeds here, so I'm gonna move on to like what is a neural network. Regardless of your familiarity, this should hopefully be like a really nice just like recap or refresh. So this is the image that you will see generally depicted of like a neural network. You see something like this, it'll have a different number of dots on each like layer is what they're called, a different number of connections. It'll look a little different, but generally this is how they're going to be displayed as. This is what a neural network is. I'm going to go over some of the anatomy of it per se so that I can use these terms without too much confusion. So this first layer right here on the left, these first like set of dots, is called the input layer. Everything in between are called the hidden layers. And finally, the last one is called the output layer. So just kind of like if I say output, know that it's towards the end of something, and if I say input, you know, it's like what we give to the network, right? And don't worry about how the data actually passes through it. That's half of this lecture. I will get into it in a little bit. But this is like kind of like how I would divide the neural network up. And as for like the smaller, like more atomic components of the network, you have a neuron, which is one of the circles. Basically, you can think of it as simply just holding a value. Most of the time, neurons are legitimately just like float values or like float values encapsulated in something with some extra methods. So very simple there. And then we have a weight, which is a line connecting two neurons that also has a value associated with it. They become very, very important because, little spoiler alert, picking the right weights is what lets the network actually learn. So that's like the basic anatomy of the network. The terms like this is relatively set in stone in terms of like everyone agrees that this is what you should call them, but you may have heard like maybe different references like multi-layer perceptron, artificial neural network. the term neural network should encapsulate all of that. So just like, this is pretty good terminology to know. And please feel free to raise your hand at any point if you have questions. So the conceptual definition of a neural network, kind of abstracting away exactly how it works, is it's a data-based function approximator. Essentially, you give it a bunch of data, a bunch of examples, and it'll try and learn a function to map the data inputs to the data outputs that you provide. So like a very, like, I guess, a simpler, maybe more understandable example that ties in a little bit to statistics is like, okay, we have some distribution. Let's just get a bunch of points from that distribution, right? And then we want the network to give us the mean and variance of that distribution, given the points. And we can sample from a bunch of different distributions, right? But ultimately, this network will learn to kind of model, like, okay, if I see this kind of like set of points, then I know that the mean is going to be shifted over, like I know the variance can be pretty high if I see a large scatter of them. There's smarter ways to do this, obviously. Maximum likelihood estimation is one of them if you know some statistics. But it gives you the intuition like, okay, I give it a bunch of data and it can tell me something about it, some pattern, something inherently true about the data and its like label, right? However, that's not why we use neural networks. We use it to classify stuff like this. This is a cat, right? And I did the 1% dog thing. It's not actually 1% dog. It just shows that, you know, like there's some, like, oh, it's very, very confident that this is a cat and not a dog. But, like, what's the function here? There's no, like, cat image to cat string mapping. That's not a real thing. It's very abstract. And that's kind of where you have to think of a different way to formulate, like, what is a function or a target-like model. You can kind of like just use the intuition you get from like, okay, here are input numbers and here is something that like tells me something about those numbers, as in like the points from the distribution and the mean and variance of the distribution, and kind of like abstract it like a level up to, okay, here's a bunch of photos of cats and here's a bunch of photos of dogs. There is on a very high level something that differentiates them, right? I can tell because I have a brain and I'm able to look at patterns and recognize them and see, okay, it looks like this is a cat, it looks like this is a dog. However, you know, we want the machine to be able to do that. And that's what it can do, and it does it on a very high level, kind of, you know, how we do it. It's like I can recognize generally what a cat looks like and generally what a dog looks like. So I'm going to do my best to put them in buckets. So that is like what a network is. It's a very, very powerful pattern recognizer. So it's so powerful, in fact, there's actually this theorem called the universal approximation theorem, and it essentially can say a neural network of an arbitrary size can model any function, which is, you know, in technicality, not a very useful thing, because it says you can have an arbitrary enlargement network, which means if you blow it up to like millions and billions of neurons and stuff like that, you can approximate any function, which is true, right? You can just have like a one-to-one mapping. But it just tells us that the style and like the construction of networks, neural networks, can perform really powerful pattern recognition. That's what I want you all to get in your head, that neural networks can perform pattern recognition if you give them a bunch of data. Any questions? Okay. So before deep learning, and this kind of ties into the machine learning lecture we had last week, you would take an image and you would hand extract some features from it. So for example, 4 could be like number of legs, 0.5 could be like weight or something. 1, I don't know, what does this have 1 of? 1 something, I don't know, right? Yeah, it could be like, yeah, so the thing is like, before we had deep learning, you would probably try and like hand extract these features on like a high level and figure out like, okay, like we did last time with a horse versus a chair, right? You know, has 4 legs, is made of wood. Those are features that we can get. So you'd hand extract them from an image. This is how you get like a representation of these like images that's very, very easy for a simple model, like perhaps like an SVM, to classify and tell you that, okay, I really, really, really think this is a cat because I see most cats have like this weight, this many legs, this attribute, has ears, stuff like that. But you have to kind of tell the model that it has those things, and then it draws a nice boundary separating them. So the features naturally kind of lie into like clusters, and the machine learning model just cuts them in half and lets you put more points into those clusters, right? it's not actually doing the separation for you. You kind of did that with the feature extraction. So deep learning comes in because we basically take the picture of the cat and say, I'm not giving you any features, I'm just going to turn you into a row of pixels, right? Literally just the raw pixel values of this image. And you feed that to the neural network, and it does the feature extraction for you basically and just spits out, okay, I think this is a dog or cat. Now you can see how that can be incredibly useful because sometimes we don't know what features are going to be important to actually classifying something. So the network can pick what it thinks is the most important aspects of an image or a data set, and then it can actually classify it based on those things. But, you know, the one downside to that is it requires a lot of data. So just to go back as like a small comparison, traditional machine learning, you hand extract a bunch of features and then you pass it to a network and it just cuts it cleanly, right? But deep learning, you can let it kind of learn the features itself. It's very powerful in that sense, right? This is what I said at the very beginning. Deep learning has more power to it. It's able to do more things, cool things like this. Any questions before we move on? Yes. Yes. So for what I meant to show by this little like transformation here is legitimately just like row by row. You take the pixel values and then just turn it into one big long vector. That's what I'm trying to represent here. The idea is that it's basically the raw image. Oh, yes.
So is there a way to like? So I know like for the standard neural network you don't have features, but is there a way to like hard code some features and like have some that are open, like kind of like a mix between an SVM and a deep learning network?
So here's the thing. If I was to give features to the network, it would make its job a whole lot easier. So say we have a really hard problem, I could give it the features of that really hard problem, and then it would then again use its power to make it tractable. So like, for example, you have a difficulty of 10, right? Like a machine learning network couldn't even do that if you gave it the features. But a deep learning network, you give it the features, it uses its power, and then can actually give you an answer. So like, I'm not saying you can't give a deep learning network like features, like a neural network features. It's just like the idea is it was made to not be necessary because the high power of the pattern prediction kind of like covers that. Yeah, I'm not sure if there's like a mix between a neural network and an SVM necessarily. I mean, neural network in itself can be thought of as a classifier. So, okay, awesome. So we're going to talk about the forward pass the network. Basically, how does data enter it and how does data go through it so that it ends up in a way that we can understand, like 99% cat, 1% dog, right? So how do we actually get, like, how does this happen? How do I give it the input and how does it get turned into an output? So I'm going to go through it step by step. And I'm actually going to use this exact same network that we've been like looking at as an example with the same like dimensions and everything. So notice how you have like 4 input neurons and then you have 5 in the next layer, 5 in the next layer, and then finally 4 in the output, right? So obviously it'll be hard to reduce like a cat into like 4 pixels. You know, we can't really do that. So just kind of think abstractly. These can be made arbitrarily long and arbitrarily deep, depending on how powerful you need your network to be. General rule of thumb, the bigger the network, the more powerful patterns it can recognize. There is a point at which it becomes a little unstable, but we don't need to get into that right now. So the idea is we have data, and then we give it to the input layer. And when I say give it to the input layer, we're going to put one aspect of the data, this data vector, right, into each bubble right there. So each neuron will now hold part of the data, right? In this case, with the four neuron input, we'd only have 4 numbers in our input vector. But like I said, if we were to expand this, it'd be possible to have a lot more data in here. But that's just like the very first step I want you to understand. Each of those bubbles basically now holds a number. And what we want to do is get it to the last layer. But before we get it to the last layer, we need to get it to the second layer, right? So we're trying to get it from there to there. And to do so, it must pass through this center web, right? So what is this center web exactly? Like I said, it's a bunch of weights, and each weight has a number associated with it. in essence, and I'll go over like how this is done exactly, you take the numbers inside of the input layer, do a bunch of multiplication and addition based on the parameters inside those lines, and then they end up in the second layer. Now, how exactly is that done? How do we go from, like 4 numbers to 5 numbers with like a bunch of lines in between? Well, it looks like this. I don't know if you can really see at the diagram up top, but I'm showing you that like you can represent that first layer as this vector of 4 going down there. It's a 4 by 1. You can consider like a 4 by 1 quote unquote matrix, really just a column vector. And then you can consider that web in the middle like a matrix of weights, right? So I'm going to show you how, if we represent this as a matrix of weights and the data as a column vector, how we can use basically just linear algebra to transform this data column vector into the next layer of the network, right? One thing to know about just like matrix multiplication in general, you're multiplying 2 matrices. You can see this is 5 by 4 rows and columns, right, with the weight matrix. And then we have the data, which is 4 by 1. Notice how there's like 4s in the middle. If you like 5 by 4, 4 by 1. Those 2 numbers in the middle need to be the same, right? So you need to have the same columns in the thing on the left as rows on the thing on the right. And you see why that's necessary, because basically what you do is you move those items and you lay them on top of this first part of the weight matrix. And then you'll multiply each blue square by like the green square underneath it, right? And that gives you a new value. And then you're going to sum all of those up, and that becomes one of your output values. We just move down, do it once, do it twice, 3 times, 4 times, and 5 times. And now look, as you can see in the top right, our goal there is to get to a 5 by 1, right? So now we've created something that looks like it. Yeah. Sorry? So it's the last row, like this one right here, right? So it's the same set of numbers right here. You can think of each of those blue ones having like a different number in it. You can literally just like, oops. You kind of see how that like flips onto it. Yeah. Yeah. And then, we go do that once, next, 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 next. So the last row is being multiplied by the same thing as all the other rows were, right? Yeah, okay. Any questions? Oh, no, sorry. This blue set of squares is separate. The weight matrix is just like basically having it tacked on. Yeah.
Sorry, but what do the blue squares represent again? Is that the input?
Yes. Yeah. Any other questions?
Is it better to think of a neural network as like an SVM, but with every single input being a feature itself, or?
When you say like an SVM, the SVM is a classifier, right? The neural network is also a classifier. They just work in different ways. So they do the same thing, if that's what you mean by think of it as an SVM. But in reality, this works off of matrix multiplies more deeply than a SVM would. So I wouldn't draw the connection too deep. They're both classifiers, yes, but this is different. It's in a different class.
So what do you mean by like deeper?
So I will get into why this way of transforming the data can get really powerful a little bit later. And if you have the same question, ask it again. Yeah. That's the matrix of weights, which if we go back to here, I don't know if you can really see that. I should have picked a darker color, but I'm trying to show you that kind of web in between the first and second layer can be represented as this matrix of weights. Yeah. So right now, I'm just showing you imagine we just have placeholders there, right? This is the physical transformation, how it happens. But how we pick the right weights is the second half of the lecture, like gradient descent and optimizing. But you can just think of this is how the data is actually passed throughout the network, assuming we've done everything correct already. Yeah. Any other questions? This is an important part to understand, and it can be a little confusing, so please ask questions.
So there's 5 different weights for each input.
Yes, yes. And you can consider that, like, if we go back here, the 5 different weights for each input, you can almost consider it. See how there's like 5 lines coming off of that top neuron? Yeah. I don't know if that makes it clear for everyone, but like take a second to kind of look at, just like in your head, that very first neuron. Notice how like the things kind of branch off of it, right? And then notice what happens to this first box at the very top. Kind of goes across every single weight, right? And then also for each output, notice how it's the sum of the multiplying each element of the input by a certain weight. I wish I had PowerPoint's morph transition to make this a lot easier, and unfortunately I didn't want to spend like 4 hours animating this, but yeah. Each node being, you're really close there. What we just did is legitimately linear regression. Like this, a layer going from one layer to the next is straight up linear regression. That is a 1-layer neural network. But I don't think what you said is exactly linear regression. Like this process is like the idea of going from like a bunch of like features to like another set through like multiplying by a weight matrix. That's actually like really close connection right there. That's linear regression from like four features to like 5 things, 5 classes, or like 5 different things. Any other questions? And please feel free to ask again if I don't hit your question on the head, because I really do want everyone to understand this. Okay, I'll move on, but let me know if anyone has anything else to say. So, and the final thing we have to do before we can officially say we've reached the next layer is squish the values between 0 and 1 with this nice special function right here called a sigmoid activation function. Why this is critical, and it is incredibly critical that we apply a function like this, not exactly just this function, but the fact that we apply a function is incredibly critical to how neural networks are able to be so powerful. So for the next 5 slides or so, just accept that this is absolutely necessary, and I'll explain exactly why. We need to apply some kind of nonlinear function to the outputs of like this first multiplication that I showed you to get like the outputs of the next layer, right? So right now you can think of a neural network as we have data here. We use this web then transformed into a matrix or like represented as a matrix to multiply this vector by this matrix to get this vector, and then we element-wise apply some fancy function to it, some special nonlinear function, and then we're here. And then what we can do is the same thing over and over again. So that's how information is passed through the network to the final layer. That process I showed you with taking the vector of like inputs and multiplying it by the weight matrix to get another vector is just repeated with matrices of different sizes that end up with that when multiplied by the input vector get you the next layer's output vector size. That makes sense. You can just calculate that really easily. Say for example, right, we're going from 4 to 5. This matrix is 5 by 4. If you want to go from like 3 to 5, you'd make it 5 by 3. Or if you want to go, you know, so on and so forth. Any questions?
So, is the operation from one layer to the next? That's analogous to operation. So is it that each node is an individual neuron, or that each layer is its own neuron, and it's just a different, like magnitude of, I guess, synaptic.
So the question was, how closely does this mimic synaptic interactions in the brain? The first thing you said was more right. Each neuron is more like, that's a connection, that's a communication. And I'm going into this on this slide. The neurons in your brain, and this is kind of the neuroscience connection I want to like display here. Neurons also implement nonlinear transformation of the inputs that it receives from other neurons and neurochemicals into binary output. Like either it sends a signal down the axon, which is that part over there that's kind of long, or it doesn't, right? And that's kind of why we employ the sigmoid function, and that's why it's a pretty natural connection. You have all these inputs coming in to each neuron, and then you squish it between 0 and 1, usually sending it to either 0 or 1. And then you have like, oh, this next neuron in the layer is going to fire or it's not going to fire, right? You can think of it like, say for example, in the final layer of our network, we want the first dot to be highlighted and the rest to be 0, right? You can kind of think how you can trace back and set up the weights such that certain inputs will ensure that that final dot is activated and the rest are not, right? You'll make sure certain weights are really high, certain weights are really low, so that you end up with the result that you want, right? And that's an example of a trained network. Our minds are obviously trained enough. I'm standing up here and I'm talking to a crowd of people, so my mind somewhat knows what it's doing. And it's able to, use the inputs from other neurons and propagate the information forward. The similarities do kind of end there, unfortunately. There's a lot more to the brain than just the simple connectome that we have set up for like the neural network. But that's why NeuroAI is so cool, because there is a lot of room for improvement on these things, right? Now the problem is proving that they're actually better, because neural networks are really good in themselves, right? But yeah, definitely keep this in mind as like why it's called a neural network. Oh, this is why. Because it does very, very on a high level mimic the interaction between like synapses and neurons in our brain, right? And that's why the sigmoid function was one of the first activation functions to be used, because it did mimic the idea of setting something to 0 or 1 as like a binary pulse out from a neuron. Yeah. Any other questions on that? All right. Okay, awesome. So the final layer, this is kind of like a implementation detail, but I think it's super useful. You'll see the word softmax being thrown around a lot. The equation for it is just up here. Basically, what it does, it just takes like a bunch of inputs and turns them into a probability distribution, right? So it'll tell you, like, for example, right, if this is what came in to the last layer of the network, like 1, 2, 3, 4 values, right? It'd be 0, 1, negative 0.5, and 0.5. You'd apply the softmax activation function to the last layer, and then these would be the new values inside the neurons. And what this means is, hey, I think that it is class B with a 46% chance, class A with a 17% chance, and class D with a 28%, and class C with 0.1, or 10% chance. So that's what softmax does, and it's really critical because what it lets us do is like actually be like, oh, network, like, what are you thinking about this image? Is it a cat? Is it a dog? And that's why I can tell you, oh, I think it's 99% sure that it's a cat. I'm 1% sure it's a dog. That's why I had that earlier, right? Softmax is super cool, and it just like kind of takes these logits, which is like the raw output of like a network, and turns it into something really interpretable. So definitely you'll see this term thrown around. Basically just means like turn these like raw outputs into a usable probability distribution. Any questions on softmax specifically? This is usually applied at the end of most classification style networks because it lets you interpret the outputs as probability and sample from them or greedily select the highest probability. So everyone understands. Oh, yeah. Yeah. So, that does one of the things that may not be true about softmax ensures that the sum of all of these will be 1. Like if you were to sum like the sum of these would be 1. I haven't calculated myself in my head, but that should be. If you apply softmax to a vector and then you sum across like that vector, it should equal 1. Now if you did ReLU or something, right, you might get 1, 0.5, 0.3, 0.7. That doesn't sum to 1, right? I mean, you could still technically interpret it as a probability, like, oh, divide it by like the sum of something, right? But that's what softmax does if you look at the equation.
Oh wait,
Yeah. So that's what I mean. You just apply, when I say applying softmax, it's doing that, like what you're probably thinking in your head. Yeah. So anything else? Okay, great. So this is gonna come back to your question earlier about like why do we need like the activation function? Why is it so like necessary to make the networks powerful? So I'm gonna introduce the power of activation functions and the importance of nonlinearity. So the activation functions, like the sigmoid one, introduce nonlinearity into like the data as it passes through the network. As you can see here, you cannot draw a line to separate the red from the blue. You simply can't. In like this many dimensions, if we're trapping into this many dimensions, you can't do that. And linear transformations won't be able to untrap this red bubble from the blue. But a nonlinear transformation can do that. So you can see, this is almost like we pass it through the network, we apply a nonlinear transformation, and it looks like this now. And now we can draw a line right through it easily, letting us classify something. So this is where deep learning becomes more powerful than machine learning. Because a machine learning model, most of them are generally going to be linear, and they can do things in linear spaces and do linear transformations, and it can, like, if you give it, like, here's a bunch of cats, here's a bunch of dogs based on some features I hand engineered. Oh yeah, an SVM could totally draw a line through there, and it can do it in, like, milliseconds, right? So no need to throw a deep neural network at it. But if your data looks more like this, here are some pictures of cats, and here are some pictures of dogs. This is what they look like if you, like, PCA them, maybe, and, put them down into, like, low-dimensional space. I can't draw a line through that, but let me transform it so I can. That's what the introducing the nonlinearities allows you to do, and that's why they're so critical. So if you had a neural network and you didn't apply that sigmoid function that I showed earlier to the kind of like the output of that matrix multiplication, you could basically just write it. Is it somewhere over here? Nope, I didn't add it. Basically, if you don't add nonlinearities, every single matrix multiplication can be recomposed into one, making it linear again and reducing its power. So again, if you don't introduce nonlinearities, the set of matrix multiplications that you do can be just composed into one, meaning you just have a linear classifier again, which again is like not powerful. So that's why it was so important, and I stressed, like, just accept that you have to include this sigmoid function here. This is why. It's because adding a nonlinear transformation partway through the network makes it such that we can do things like this, right? And some of you who might be familiar with machine learning might say, okay, you can do the kernel trick to pop it up and slice it. No, we don't do that here. We're going to just like, I understand that is a very valid reason to use, like, the kernel trick and actually split the data that way, but I'm trying to make a point here, so let's forget about that. Anyway, so here are some other activation functions, and you'll notice that, oh, sigmoid isn't highlighted. Oh, I thought that was the one, right? Turns out it's actually not that good as an activation function. The way that its derivative is not, okay, if you derive the sigmoid function, you will get something in the shape of a little hump over the y-axis, and that's actually not super conducive to updating the network as you try and calculate weight updates, and I'll go over that in a second. Long story short, sigmoid doesn't really do well for updating the network. Like, yes, it introduces nonlinearity. Yes, it's very similar to like how the brain would handle things with like shooting out like a yes or a no signal. But in practice, it doesn't work. That's what I kind of mean. It's like an empirical science, right? We picked it because we thought it would be great. Oh, it turns out it's not so great for like these certain reasons. So we picked this one, ReLU. It's legitimately just like max of 0 and x. That's it. It's a line here, y equals x, and 0 all the other times. And this is like the default choice because it works so well. So you can kind of see the nonlinearity doesn't need to be like insanely strong. Like, this seems like a linear function, right? But it's non-differentiable here. Obviously, this is a line, but the whole function is not linear. So yeah, but you need to always introduce a nonlinearity. This one seems simple. It's easy to calculate, like gradients for, and it works really well as a good first choice. So in the assignments later this week, you will be able to play around with different activation functions in PyTorch and see how they impact the learning of your network. So here are some examples, right? Like ELU, TANH, leaky ReLU. That one's pretty cool. Sigmoid, we don't like it. And normal ReLU. Yeah.
Sorry, but why did you say sigmoid wasn't very good?
So essentially, okay, I'll do like a little thing over here. This isn't like super. I don't know if you can you see what I'm writing right here? Oh no, you can't. Okay. If this doesn't work, I'll just try and explain it by hand. Okay. Well, essentially, the problem is that like when you're updating a network, you need to be able to pass gradients, which are how you want to update the weights of the network so that you can learn better or actually fix the problems with your network currently. You need to pass that back to the network. The way sigmoid's derivative is shaped kills those gradients so that the weight updates stop after the first couple layers towards the end. Essentially, it'll just like, okay, great, everything passed forward, great. Now let's kind of go back and update the weights to adjust our network, right? Because of just like the math of how the sigmoid function, like this derivative is shaped, it'll just kill it. It'll send all those gradients to zero or something really close to zero, just by nature of how it looks. And I mean, you can't really see this, but like I don't know, sigmoid kind of looks like this. Its derivative is like that. So if you have values over here, they get sent to zero in the gradients, and then nothing updates. That's the short answer, but we can definitely talk about it more afterwards. And that's why kind of Raylu came along, because it's like, okay. Thanks, Amaya. All right, awesome. Now we're going to go over backpropagation and how exactly these networks learn. I won't get like super into this because the 3 blue 1 brown video linked in like the lesson can do an amazing job with like animations and stuff, as I said, but I'll try to give you like a high level intuition for like what happens, right? And understanding backpropagation is actually, I found like before, if you asked me like a year ago, I'd say, oh, you don't really need to know. But if you kind of know like how it works and why it breaks, you can really make intelligent network designs, because you'll kind of realize like, oh, it's not working because, like I said, the sigmoid function's derivative is kind of like flat in certain areas and it won't pass gradients backwards. Like you can start picking out things like that. So while this stuff isn't necessary to complete the assignment at all, I think it's super interesting. So our idea is to find the best W matrices, right? So here are the 4 matrices that we need to like actually pass through our network, right? We saw the first one takes us from 4 to 5. The next one goes from 5 to 5, 5 to 5, and then 5 to 4. Yeah, those are the 4 like weight matrices that you'll need to actually like tune to solve the problem. This is all based off that image I've been showing throughout the lecture, by the way, right? So you can see this is like not that many parameters. Like you can just kind of like count them. You can see how many there are. You can just like, you know, check out how many there are in your head. But we need to basically find numbers for each one of these squares that are so perfectly selected such that if I give the network input, it'll actually classify my image properly, right? Which you might say like, okay, obviously brute force, that's impossible, right? First off, the search space is infinite, like, and even if you were trying to make it like smart search, you won't find the perfect weights and yada yada. You don't want to do brute force search. Like, how do we actually make it so that, oh, okay, this network will intelligently classify the items I give it? So let's just start off by, despite everything I've said, let's start off by randomly initializing them, right? And just seeing how our network does. So here is the output from an untrained network, right? It just spits out something silly. You give it a cat and tell me, is it a cat, dog, train, car, or a mea? I don't know, something, right? So some like set of classes. And it says, okay, yeah, I think that cat you showed me, I think that was it. What did I say? Truck? Something like that, right? The network thinks that cat is a truck. I don't think that looks like a truck. So obviously it's not doing so well, right? But we know what that's supposed to be. We have labeled data of like, oh, that's a cat, right? So we have, this is what we'd actually want to see. We want to see that cat kind of like node, the one that tells us this is a cat, to be the highest and everything else to be 0. That's what we want to see. So how do we like quantify how poorly our network performed on this like test? You take the vector, we'll call this y hat, it's prediction. You subtract from it the ground truth vector, right, to get this. You square all the values and you sum them. And this right here is called the loss of that like forward pass, the loss of the function. which is critical for letting you know how good the network did on that one pass, right? So can someone tell me, would a higher loss, like what would a higher loss tell you versus a lower loss? Can someone let me know? Exactly. Yes. 100% correct. You want that final number I showed over there to be as low as possible. And there's no like really ground truth reference. It really depends on like what your data looks like and what you want the ground truth labels to be, right? In this case, like 0.86 doesn't seem like a big number, but clearly we're far off. So you want it to be like 0.00001, something super low, right? So that would be what we're aiming for, but we're not there yet. So how do we actually, now that we've kind of reported this number back to us, okay, we're not doing so good, how do we improve the model? So what I showed you here was like the mean squared error loss function. That's just like this, the formalization of it. Basically, you put a bunch of examples in a batch, is what it's called, and then you pass them through the network, you calculate this number for all of them, and you sum them all up and average it. And that tells you generally on this chunk of your data set, your training data set, how well did the network do, right? And you want that number to go down each time you update the network's weights so that you can tell that it's getting better and better and better, right? So also in the previous slide, you saw I summed it up, but usually the computer won't do that in the background because you need to keep them separate to like actually do backpropagation properly, which is what I'm going to go over now. So the intuition behind backpropagation is that you have basically this thing called a loss landscape. It tells you like for each configuration of weights, what will the loss be in general, right? Now, even for a basic network, it's impossible to visualize because you'll have X, Y, Z, W, all these, you'll have like a bunch of axes, right? So this is an example of like just a two-parameter network, which is, it's basically nothing, right? You have, here's like the first weight, here's the second weight, and then how high or low it is tells you like how good or bad the network did. Obviously, we want to land here. We want to be here. We want to select the coordinates of like the weights that let us get the lowest loss possible. But we don't want to. You don't want to end up there at the top at the red, right? That means you're doing terrible, right? So say we randomly initialize like here or something, right? We want to slowly make our way down this hill to end up in like this pocket over here. That's what gradient descent is. You're descending towards this minimum. And again, it won't look like this. It's impossible to visualize what the actual loss landscape is, even for a simple network like the one I showed you earlier, because of just how many like parameters there are. You'll be getting into like 90 dimensions basically, right, and beyond, like, and then you'd have like one output. It's impossible to visualize, but that is genuinely what is going on in the background. You try to find like the set of weights or values for the set of weights such that your loss is the lowest, right? So you want to make your way down there, assuming we initialize randomly at some point on this loss landscape, right? So one important like calculus term that you need to know is gradient. The gradient of a function is essentially a vector telling you if you were to step in this direction, you will increase the value of the function the most, right? So these arrows tell you like, oh, like if you were to go this way on this function, the ultimate result would like spike a lot, versus like if you were to go some other way, it wouldn't go up as much, right? If I'm standing in this big bowl, right, if I step like maybe a little bit this way, it won't do so good. I won't like go up that much. If I step this way, I won't go up that much. But if I go like right ahead of me with this big slope, my height is going to increase a lot. That's where the gradient is going to tell me to go. But we don't want to get like super high. We want to go super low. So we're just going to flip the gradient on its head and go that way, descending towards the optimal minima. So that's the goal, right? Before I get into like the actual math of it, anyone have any questions based off like the intuition? Like what are we trying to do? Like how are we trying to step towards the minima?
So are we like taking the partial derivative of the loss function with respect to each weight?
Yes, exactly. That's what this is. You are legitimately going to be taking the derivative of the loss function with respect to each weight and then updating each weight based on the calculated number that you get out of that, right? That you just explained backpropagation. Yeah. So now how that's done exactly, you might be thinking, oh, but like, how do you calculate that? There's a bunch of equations going on in there. So ignore this big wall of math. Let's step through it bit by bit so it's actually interpretable. Here's the dummy network that I've set up. Here are the values of A, B, and C as your inputs. Weight 1, weight 2, and weight 3 highlighted in bold. And here are the dummy outputs and the ground truth that we want. Take a quick second to absorb that. What the problem statement here is. And we want to say like, okay, how do we update the weights so that next time I see A, B, and C, it'll look more like this and not like this. That's what we're trying to do here. We're trying to find that upside down triangle is nabla, which is just basically the gradient of the loss function with respect to the weights is kind of implicit. So we want to find partial L over partial W1 and then like W2, W3, so on and so forth, right? And a fact, the chain rule of calculus or chain rule derivatives tells you that you can decompose one of these derivatives, del L over partial W1 into the derivative, partial derivative of the loss function with respect to y hat of I times the partial derivative of y hat of I with respect to W1. So basically it's just like, you're like, I can't, damn it. See, you're like, you can think of it, I know you're really not doing this in math, but like you can think of it as almost like canceling those like y hat i's. That's the way it works in my head basically. But that's a chain rule. You can decompose that one derivative we're trying to find out into those two. And then we can actually calculate those two like separately. So first we want to find derivative of the loss with respect to y hat I. That's those two lines right here. It's pretty simple because partial derivatives let you just like disregard all the other variables essentially because they're treated as constants. So you can see that this is the result of that. And then you have, okay, how is y hat of I calculated? A times W1, A, the line W1, plus B times W2, B, the line W2, and then C W3, right? And then if you take the derivatives with respect to the first weight, the second weight, the third weight, you'll get A, B, and C respectively. Then you just multiply those two together, and this is like how you would calculate the loss. Now, I'm not saying that this means you can do like the gradient update for a network by hand. I mean, you could if you really wanted to, but like you have so many better things you can be doing with your time, right? So I'm just showing you like sometimes, like when I learned this stuff first, I thought it was magic. Like how can a network just like calculate how to classify a cat? Well, if you look at the dummy example, you can see that a calculation really isn't like intractable. It's very much possible. But obviously you scale it up a lot. Some tricks happen. You just need to keep in mind. Just keep in mind that at the end of the day, it's like what happens in a neural network is basically all just multiplication and addition with the nonlinearity thrown in. And if you pick ReLU, it's legitimately just a max. So you have three operations in a neural network: multiplication, addition, and a max operation. And that can classify cats from dogs and trucks. It's kind of incredible, right? So this is just kind of like, you can pick this apart later if you want to check out the slides, kind of understand like how I did this, like why there's certain, like I made certain choices, like why I split it up into two different derivatives. But this is just an example to show you that this is like a tractable problem and it's not just like magic, right? Like the math you can write out by hand if you would like to. Now, throw that all out and then look at this bottom part right here, right? Once we've calculated the partial derivative of the loss with respect to the weights, you want to, because that's a gradient and we want to step the opposite direction, you subtract that from the old weights to get the new ones. But then you might be asking, what's this little like lambda term right here, right? So I'm going to get into that in the next section. We're almost done, by the way. So this is like one of the big takeaways I want you to understand. It's just like, it's not actually magic. There are like set rules to updating. Before I move on, any questions on this? There has to be. Yes. So you always want to be going down. So the reason I said like you want to go, the gradient shows you the steepest way. So if you want to find the way down, you invert it and just go the other way. That's what I mean by descent, right? So someone's like, that's the way up the tallest mountain, but you're like, no, I want to go the other way. So then you just, and turn around and walk that way. So that's why it's like gradient descent. The gradient, just by definition, is the positive direction, and you want to go to the negative direction to like the pit. Yeah.
So if like there's multiple like saddle points, how do you get to like the deepest saddle point?
Yes. Okay. So this is like this. You're asking really good questions, but that will be answered on the next 2 slides or so. So yeah. And I have a whole slide on that. Yep. Anyone else? Any just like comments, something you want to say? Anything at all? Okay.
Figure out the best, most optimal path to avoid this, figure out like ways which are better than your previous iteration. And like unfortunately this, I'm sure you'll get you'll be talking about this, but unfortunately this leads to you not necessarily getting the best possible model, but like it gets a good enough model.
Yes. Thank you for bringing that up. We'll go into like why that's the truth in a bit, but then Kellen?
Yeah, I was wondering, since you've been doing this for so long, can you do this in your head now?
Yeah, actually, no. I just did this. No, absolutely not. That's it took a lot of watching videos and giving this lecture a bunch of times before I can just like whip this out and write it on the board. But I wish I could do this in my head. I think I'll be doing some pretty cool stuff if I could. But no, it definitely is definitely something you have to think through. But the computer does it for you, so you don't have to do this. You don't do this in your head. Thank God. So, anything else? Yeah. Oh boy, you opened a whole box of worms. Reinforcement learning uses neural networks very deeply. I could go on a huge tangent about this. We can talk after for sure. I'll answer that question exactly. But let's move. Let's wrap this up so I don't keep everyone here for too long. So one thing about the learning rate, the lambda that I was mentioning earlier, and its importance is basically, okay, you have these gradient steps, right? But how big do you want to take that step? You basically like can see that this is the way down, but you know, if you go too far, you'll end up on the other side of the pit. You won't go down it, right? So that's why you want to pick the right learning rate. So if the learning rate is too low, it's going to take forever to get to the bottom of the pit, right? If the learning rate is solid, you'll like quickly go down the slopes and you won't overshoot the pit that you're trying to enter. If your learning rate is high, you'll bounce around and never actually reach that like optimal minima. And if it's way too high, you'll actually get worse despite this calculably giving you the best way down, you'll actually get worse. So like when I was like training networks, I was thinking like, why is my network getting worse? I thought gradient descent was supposed to always give me the optimal solution. No, there are like other considerations you need. It is really cool, but again, it's not magic. It's not going to solve it for you. You need to like tune these parameters so that you can actually kind of make your way down to the pit properly. Right? And now I'm going to get into what you two were talking about. Machine learning. Oh, were people taking photos of that, by the way? Yeah. Oh. Yeah.
My question is, what happens when gradient descent finds a local optimum instead of a global optimum, and is that something we can kind of work around?
Mm-hmm. Yes. So, okay. Everyone's talking about this now. This really good point I really wanted to hammer home. Thank you, Maya, and thank you too as well. One of the big differences between machine learning and deep learning, right? Just like Amaya said, in deep learning, the loss landscape is non-convex, which essentially means that you can find local minimas which are not as good as or low as global minimas. And you can basically get trapped in them, right? If you're at the bottom of a pit, you can't see the other pits around you that might be deeper. So you'll be standing in this one and thinking, I reached the bottom, I'm optimized fully. But if you were to climb this huge hill, maybe you'd find a deeper pit, but you don't know that. And gradient descent, like, there's definitely like ways around it, but you have to think like, oh, okay, the update is going to go towards the like the next like deepest slope, right? If your random initialization puts you near a pit that isn't optimal, you're going to end up in that pit. And maybe the most optimal one is really far away. You didn't initialize properly. Maybe you should have taken a really big leap at some point. Whole bunch of things. And this is where like hyperparameter tuning comes in. You want to make sure like the learning rate is high at first to bounce around all over the place, but then settles down once you think you find a right spot. So that's like a big thing, right? You don't have the same theoretical guarantees that you do with machine learning. With most machine learning problems, the loss landscape is convex, meaning that once the model has been optimized and the loss kind of flatlines, you know you found the best possible solution given that model for that problem, right? Meaning it's like fully optimized and you know you can't do much more. With a neural network, it's like, maybe I can optimize more. What if I add another layer? Maybe the loss landscape will change in such a way that I can get deeper, right? So like that's the big thing I want, like the takeaway about like deep learning. It's super powerful, but a lot of the guarantees go away. And you can find that either exciting or annoying. You can find it exciting because now you have a lot more to experiment with, or you can find it annoying because you'll never know if you're doing the best you can. And there's always going to be little tweaks you can do to make yourself 1% better, you know? So like that's one of the definitely like the big things. Machine learning, a lot of theoretical guarantees due to the convexity of the problems, but the deep learning, a lot of the things are non-convex, so you can't provably show. It's basically, to my understanding, provably impossible to show that you are in a global minima, like with a neural network, especially if it has a lot of non-linearities. You kind of just have to do a bunch of experimentation. So if someone somehow has come up with a proof for that, talk to me outside for sure, please. I won't steal your work, I promise. What else is here? Yes. So this is not to say that machine learning isn't powerful. If anyone's messed around with gradient boosting models, with Kaggle or anything, LGBM or XGBoost, like they're really good. They're really, really good, and they can fit fast. But if you want like deep, strong, like real, super cool power, that's usually where deep learning lies, with transformers and such, right? Again, super data hungry. That's another thing that you want to make sure you know about deep learning, right? That's why you need a bunch of examples in your training data.
Why does deep learning require a GPU?
So the little thing, like GPUs were made to do basically matrix multiplications for like ray tracing in games and stuff like that. I don't know if ray tracing is the right word, but basically just like to create a 3D engine, you're doing a bunch of matrix multiplications, a bunch of linear algebra. We repurpose GPUs for machine learning and deep learning because we're also doing, as shown, a bunch of matrix multiplications. That's not to say that machine learning doesn't also benefit from a GPU, but deep learning is like basically predicated like on the fact that you're doing a bunch of matrix multiplications. So that's why GPU speeds it up like from basically impossible to like possible. Any other questions? Yes. Yeah, so like if you're in that little like pocket though, and you don't do something to your learning rate intelligently, you will stay there. Unless you increase it a lot, then you'll start bouncing out of it, right? But say but the thing is, like I said, you don't know if you're in a global minima. You're just like, I'm doing pretty well. Is there something deeper outside? Does it require me to do like a big leap? I don't know. Yeah. Mm-hmm. Mm-hmm. Are you talking about like cross validation, like training with different hyperparameters and then picking the one with the lowest validation? Yeah, that's a good strategy. But again, like even the best one of that, could there be a better one? Right? Like you'll never like know. But there are ways to like show that you're getting better, right? It's not like it's a, oh no, sad, throw out the whole field. No, like people are working around around this in smart ways. All right. So like I have a sandwich, and I have a hydrogen bomb, and I have a knife. What should I use to cut my sandwich? Right? Like, can someone tell me what I should use to cut my sandwich, please? Yeah, you're right. Totally, totally. Wonderful, wonderful scientists in the future, right? So this is like kind of the analogy I like to say. Your data is the sandwich, deep learning is the bomb, and machine learning is the knife, right? So don't use a bomb to cut a sandwich. It's not necessary sometimes, right? You could say that Kevin Jameson, who teaches 446 here, got to me because he definitely drilled this point home that like you don't always need deep learning. I'm trying to instill that as well. Deep learning is super cool, super powerful, and for certain use cases, it can blow machine learning out of the water. But most of the time, especially if you experiment with this more and more, you'll see that it comes with a lot of problems. And obviously, there's a whole field like dedicated to trying and solving those problems, right? But just I want to drive home kind of the idea of the difference between machine learning and deep learning. Linearity, convexity, theoretical guarantees, empirical science, really cool, powerful stuff, but not as many guarantees on what you're going to be able to do. So yeah, and with that, do we have any questions on deep learning and neural networks? No? Okay, awesome. Thank you, everybody. That was really good. Yeah. Amanda, do you have anything to say, or is this? All right, awesome. Feel free to talk with your TAs or head out. Either one's fine. And let me know if you have any questions.